Hello everyone, and welcome back to Reverse Engineering Linux 32-bit applications. In this video, we're going to continue our discussion of heap buffer overflows, and in particular, we're going to show you some simple examples. So let's go ahead and get started. I will begin by bringing up my text editor. And I will create a nice simple heap overflow like so. So my C program is going to start with some includes. Start with standard IO, standard lib. And I will go ahead and make this a little bit larger. And I will also include string. That'll allow me to use things like stir copy. I'll create a main method, which will take an arg count and a set of arguments. All right, so we said that in order for there to be a vulnerability, in most cases, I need to allocate 2 chunks of memory at a minimum. So let me go ahead and do that. I will just create some character pointers or string pointers, if you will. And I will call them P1 and P2. Then I will go ahead and allocate some memory. So I will say P1 equals malloc, and I will give it a size, and I will give it a size of 16. I could give it something larger, but there's really no need. And P2, I will give that a size of 1K. So now I have 2 different buffers, and what I want to do is trigger a vulnerability, create a vulnerability. So I will do this. I will say if my argc is greater than 2, actually greater than 1, or I could say greater than or equal to 2, then I will call stir copy, and I will give it my destination of P1, and my source will be argv1. Recall that argv0 is the name of the program that you're calling. So now I could do other things in my program. My program's going to run, And what's going to happen? I'm going to free my buffers when I'm done. So let me go ahead and do that. And I will return 0 to indicate success. So this is a dirt simple program. It doesn't really do anything other than create a heap buffer overflow vulnerability, of course. So this is my simple little program. Let me save this. I'll hit Control S, and now I need to build it. So recall that if I want to build this, I can use GCC making the font a little bit larger for you here. So I can say GCC, and I can give it heap.c -o heap, and I could just go with that. Now, what this will do for me is it will create a executable, but it's not the executable I want. Because if I do file on heap, it tells me this is a 64-bit executable. So notice that by default on my 64-bit system, of course, it has created a 64-bit executable, which is not what we want, at least for this course. One other thing you might notice here, I ran file and it says that it's not been stripped. We'll get more into this later, but stripping will take away certain symbols that can make it easier to reverse engineer an application. Of course, if you really want to make it easy, you're going to create a debug build where it has all kinds of debugging information built into it. So how do I fix this? Pretty simple. I just add -m32. And now if I rerun my file command, it says it is a 32-bit application. Great. So now what? Now I want to run this and see if I can get it to fail. So if I just run it normally, just say heap, it runs. And because of my little check that says, did you have an argument? If you did, call stir copy. And I didn't in that case. So let me rerun it. I'll give it a few A's. And it runs just fine. What if I give it a few more? Now, not so fine. So now you'll notice that it core dumped. So it was a bit unhappy. So what happened? Well, this is where you can run it through a debugger. So let's go ahead and do exactly that. And we're going to run Evan's debugger. As a reminder, if you don't know how to run something, you can try to run it with --help. And here it says I can use --run and a program with arguments. So let me go ahead and do that. edb --run /heap, and I will give it a few A's, a few more than I should have. And we will see what happens. So I have my program. Look at my preferences. And of course, I'm going to up this font quite a bit. So that you can see it. And what else will I do? I will analyze. And so now I can see my various sections. I see my registers, my stack, and the various parts of memory that I can dump. And then here I have my source code. So let's go ahead and step through our program. All right. And here you'll notice that it says I'm going to call into heap. So of course I was in my boilerplate code, if you will, before. So I want to go here. And I will start stepping. So here I can step through my program. Now, if I wanted to, I could just go ahead and say, just run it and see where it's going to crash. So let me do that. So I just ran it and let it go. And it says it was aborted. Well, where was it aborted? That's the question. It says return from syscall, tg kill, and here's where I was at. So I could unwind the stack and use that to figure out where I ran into trouble. So I have a few different ways I could figure out exactly how this is crashing. So why am I trying to figure out how this is crashing? There's a couple of reasons for this. Depending on what I do will determine where it's going to crash. You might say, well, what does that mean? What that means is that I can cause it to crash either in the free call or possibly in strcpy itself. I don't want it to crash in strcpy. I definitely want this to crash in the call to free. So how can I do that? Well, let me go ahead and exit this. I'm going to rerun it. But this time I'm going to start out with just a few A's. This is something that should not cause a problem. All right. So let's go ahead and start stepping. And let's do our analysis. Once again, if I look at my different memory regions, I'm going to see I have my program. It has the text segment that contains the code as a read-only segment for data and a readable and writable segment for changeable data. And this started at 08048000. And here I can find my functions. That are being called. And you'll notice I'm calling free, strcpy, and malloc. And a few other functions as well. So this can be helpful if I want to find these various function calls. All right, so let us continue. And here we are. We have our first call to malloc. And of course, it's not going to call it directly. It's going to use the PLT. We talked about that in previous videos. So I'm going to go ahead and step over this. I'm going to add 16 to my stack pointer. And I'm going to call heap malloc PLT again. So this is my second allocation. Now notice here, my first allocation was for 16 bytes, which is hex 10. My second allocation was for 1K, which is hex 400. So again, if I look back at my source code, here's my first malloc for 16, second malloc for that. So let me go ahead and continue. And I have a pointer now to both of those items. Here's my test to say, did I give it an argument? I did. Now EAX contains the location for all of my A's. I'm going to push that on the stack. And I'm going to go ahead and put my location on the stack as well. Location for what? This is the location for my stir copy, my destination. Recall when we talked about function calls and calling conventions, we said that by default, if you're using cdecl, you will take all of your arguments and you will push them on the stack from right to left. So this is my location, 08A13008. And that is the place that I am pointing. So let me go ahead and have a look at that memory location. And notice it says this is a heap. And I'm pointing at A13008. So I should see these values appear here momentarily if I continue. So we go ahead and step over this. And there you have it. I have these values appearing on my stack. Now you might ask yourself, what are some of these other values? Some of these other values are going to point at these internal structures for my stack. And that is where I can run into some trouble. So what are these internal structures? Well, in the case of Linux, when it is doing this allocation for my chunk, it will store a previous chunk size and a chunk size at my location. So this is the first chunk. So first chunk starts at 3008. And then there is 16 bytes. So here is where it starts. Here's where it ends. After that, I have some values for my previous chunk size and my current chunk size that are stored here. So my previous chunk size and then my current chunk size. My current chunk size in the case of this guy, the next one, is going to be a size of 4 0, and it's not 0, 0, as you might expect. It's 4, 0, 9. You might say, what's with the 0, 9? Well, there's a little bit of overhead in this. Don't worry about that just yet. Okay, so I'm just going to go ahead and let this program run. Before I do that, I'm going to add a breakpoint here for future purposes. I'm going to give it F9, and it says, hey, this thing exited normally. Great. Well, let's rerun it. We've seen previously that this argument editing doesn't work terribly well in the case of Evans debuggers. So let's just go ahead and do this. I'm going to rerun it, and this time I'm going to give it a lot of A's. How many is a lot? Well, a lot is more than enough to get past this buffer. Now, I suppose if I really wanted to do this the super elite way, I might have done something like used a Perl or a Python script here. For now, we're going to do it the super simple-minded way. All right, we'll try that. So I will go ahead and I will just run my program up to my breakpoint. And it said, hey, I didn't like this memory address. This doesn't seem to be mapped. So what happened? Well, let's do it a little bit more slowly. So let me go ahead and restart it. And now let's go to our calls to stir, copy, etc. And again, we could use our function finder, make this a little bit easier. And here we are in our main method, allocating 16 bytes or hex 10, allocating 1K, doing our check for our command line arguments. Okay, so now we're getting ready to call stir copy. So let me call stir copy. I'm going to step into this. So inside my stir copy, I'm going to go ahead and do this actual copy operation. So what's it doing here? You'll notice what it's doing is that it is slowly copying chunks of memory. So you'll notice how ECX is increasing and increasing. And what happened? I had an access violation. Now I can look at my instruction pointer. Where's that pointing to? It's pointing inside of libc. So here's the issue. It crashed because it crashed in the stir copy. Why did it crash in the stir copy? Because I so grossly exceeded the boundary of my buffers. I didn't just overflow the first buffer into the second buffer. I overflowed the whole thing. So if I go back to my program here, I had 16 bytes and then I had a kilobyte plus a little bit for my underlying structures. And I overflowed the entire thing. So I got into a memory area that didn't belong to me. And it said, whoa, I'm sorry, but that's a problem. And I'm going to crash here. I went too far. But if I don't go so extreme, I can crash this sucker and crash it in the free, not in the stir copy, because the stir copy crash is not exploitable. Let me say that again. If you crash it in stir copy because you accessed memory that wasn't available, that is not exploitable. If I overflow into the next buffer, that is potentially exploitable, either by causing a crash at free, or by overwriting some values that are going to redirect my function. So let me show you, just to be clear, what I mean by this. Go back here, and I will exit. And this time, I'm going to be a lot less extreme about it. and I'll say 16. And then I'm going to have 4 Bs, 4 Cs, 4 Ds, 4 Es, and 4 Fs. And that's it. So I'm just going to overflow into the next guy. So let's see what happens now if I do it this way. EDB -- run. So let me go ahead and step. All right, so here we are back at our main function, getting ready to call malloc first time, second time, and now we're calling stir copy. Now in this case, I'm just going to step right over the call to stir copy, and boom, it copied everything and it was just happy. So now what? Now if I continue, I'm going to have a crash in my call to free here in a couple of lines. Incidentally, you'll notice that I'm a byte off, probably because of null bytes, or I just miscounted when I was entering that on the command line. So now if I do this, I can step and it's going to be very unhappy in this free. And there you go. It says, whoa, I'm sorry, but I didn't like that particular address that you used. And that's going to be a problem for So again, it crashed right here. Let me do this, but not running it through EDB. Just going to run it directly. See what it says. And it gives me a core dump, and it gives me a little bit of information about what was being called when it dumped the core. It says, here's the backtrace, invalid pointer, and here was the pointer that it tried to use. Okay, so I think that gives you the basic idea, at least, of what can happen if you have a heap buffer overflow vulnerability. This is, again, just a very simple example. We will look in depth at some slightly more complicated examples and how I could cause them to be redirected and do something a little bit more useful than just crashing a program and possibly causing a DOS attack in future videos. But that's essentially what we wanted to talk about in this particular video. Now, as a reminder, this video is one in a family of videos here at Pentester Academy, which is your source for everything InfoSec. So we have classes in pretty much anything you would ever want, new classes coming out every day. And I look forward to seeing you back in this course or another course soon. See you then.